Well, hello crew. This is our Unit 1-2 notes where we are going to look at the types of functions that we're going to study throughout our year in pre-calculus. Let's start with what we already know. We know the definition of a function. We've learned the formal definition that says if y is a function of x, then for every x there is one and only one y. Right? What we have here says the same thing, but in a little bit of a different way. It says that a function is a set of ordered pairs, that is points. Remember that any set of points is a relation, but a function is a special relation where for each value of the independent variable, that is our x, right, there is only one and only one corresponding value of the dependent variable, that is our y, in our range. Because of this definition, the graph of a function will pass the vertical line test. That should be a test that you're familiar with. So if I were to look at the graph of a relation, and I were to take this graph, right, and draw any vertical line, if that vertical line would intersect my graph at one and only one point, which this line does, and that would be true for absolutely any vertical line. So no matter where I draw my vertical line, I only have one place where each vertical line intersects the graph, right? Then for every x, there is one and only one y. The vertical line test corresponds to the graph of a function. Okay. In contrast, if I were to look at this graph, and I were to draw a vertical line here, okay, I have a vertical line here that actually intersects my graph in not just one, but in two, three different places. So for one x, right, let's say that this vertical line is located where x is 3. I have 3 points, each with the x coordinate of 3. But the y coordinates of each of those points are not the same. They're different. Right? This might be 5. This might be 1. This might be negative 5. Okay? This is not the graph of a function. Other terms that we should be familiar with when we talk about functions are these, right? We know that graphs have intercepts, and when we talk about intercepts, we're talking about lines that the graph intersects with. A y-intercept would be the place on the y-axis where the graph crosses. That's going to occur where x is 0. Right? An x-intercept is going to be a place where the graph crosses the x-axis. That's going to occur where y is 0. We know that a function can have only one y-intercept, but could have any number of x-intercepts. If we come back and we look at the graph of the function that we drew above here, we can see that this graph has one y-intercept, right? That's our y-intercept. But it has an x-intercept in 3 different places. So one x-intercept, a second x-intercept, 3 x-intercepts. Another thing we're familiar with is function terminology, f of x terminology, where we use f of x as a substitution for y. We know that in function notation, any value or expression, right, so any single number or any mathematical combination of numbers, in parentheses following the function name, right, generically we use f, but it could be any letter, is used as a substitution for x. So if I have that f of x is equal to x squared plus 5x plus 3, right, then what I know is the x is holding the place of my input. So I could even rewrite this as a place for my input gets squared, plus I'm going to multiply 5 by, right, the value of my input, and then I'm going to add 3. So if we need to find f of 4, we simply put in 4 where x was holding the place. So I would have 4 squared plus 5 times 4 plus 3. If I evaluate that following order of operations, I square my 4, 16, then I can do my multiplication. 5 times 4 is 20, plus 3, and I get that f of 4 is 39. So that's a review of terms that we need to be comfortable using, right, as we're communicating about functions together. Right? The next thing we're going to look at is the names of the functions that we will use over and over again this year. Right? One thing to know about the names of functions is that functions are named for the mathematical operation that's performed on the independent variable x. Different types of functions have similar graphical features. So we're going to look at a table where we look at the basic form of different types of functions. Okay, in these descriptions, x is going to stand for our independent variable, f of x for our dependent variable. So again, f of x taking the place of y. All other letters are going to represent constants, so numbers that would not change for a particular equation. So I have information arranged in a table for you. What I want to point out to you is that in this table there are certain things that you need to know. The other information is good, but when I'm holding you responsible for these 3 things, you need to know the name of a function. We need to all call functions the same thing. You need to be able to recognize the general equation of a function, right, and an example of that type of function. And then finally, you need to be able to recognize the graph. So these 3 should be paired together. You should be able to go from the name to the general equation to the graph or in any other order. So let's dive in. We'll start by talking about a polynomial function. A polynomial function is an equation that is made up of power terms that are added together. So our variable has an exponent, may or may not be multiplied by a number, right? And those separate terms are added together. In this case, n is the largest exponent that shows up on x in any individual term. If n is 3, we call the polynomial a cubic polynomial. If n is 4, we call it a quartic polynomial. If n is 5, it would be a quintic. If n is bigger than 5, you can just call it a 6th degree. So if n is 6, it would be a 6th degree polynomial. Here is an example of a polynomial function. 2x cubed is our term that has our highest power on x. So this is a cubic polynomial. The typical graph of a cubic will take this shape. We'll take this sideways S-shaped curve, where a cubic or any polynomial function will have up to n x-intercepts. So for this, n is 3, and you can see that this graph has 3 x-intercepts. It will have up to n minus 1 vertices. If n is 3, n minus 1 is 2. And this graph has 2 vertices, right? One at the top of this hill and one at the bottom of this valley. The domain of this function would be all real numbers. This extends for forever, right, to the left and to the right. The second type of function we're going to talk about is a quadratic function. Quadratic functions are actually special type of polynomial functions. We look at them so often that we'll use the name of quadratic over the general polynomial because it's more specific. Those polynomial functions will take the form of ax squared plus bx plus c. This is an example of a quadratic function. So one thing you'll notice from this example is our a value, our coefficient of x squared, is negative. It's negative 2. Right? If a is negative, then the graph of a quadratic will be an upside down parabola. If a is positive, the graph of our parabola would be right side up. Okay, so happy versus sad. Okay. So in a quadratic, n is 2, and you'll notice that this parabola has 2x intercepts, and it has one vertex. 2 minus 1 is 1. And the third type of function we're going to look at really would be in the form of a polynomial function, but it is a linear function because the highest exponent we have on x is 1. The form is ax plus b. You might be more used to looking at that as y equals mx plus b, and this is an example of a linear function. F of x equals 2/3 x minus 1. When we graph linear functions, you've been doing this for a long time, you know that the constant in that function is our y-intercept. So we would know that this graph would cross the y-axis at -1, and the coefficient of x, right, that's our m in this form, is our slope. So if we were to graph this equation from a point at -1, we could go up 2 and then to the right 3 to get a second point. So the graph of our this particular linear function, right, this is f of x equals 2/3 x minus 1 would be this line. That's our first 3. Let's look at 3 more. A direct variation function is actually a special type of linear function. It's of the form f of x equals ax. This is an example. Right? And the features of a direct variation function is that the domain is typically from 0 upwards, so we have no negative values of x. Right? So the graph of f of x equals 4x would start at the point 0, 0, because 4 times 0 is 0, and it would extend just to the right with a slope of 4. The next type we're going to look at is a power function. A power function is actually a special type of polynomial function where there is only one term. You'll notice that in our power is made up of a base, right? This is our base, and an exponent. B is our exponent. X is in the base of that power term. F of x equals 2x cubed would be an example of a power function. Right? These, like our direct variation functions, typically have a domain of x greater than or equal to 0. And if b is positive, then the graph of a power function would look like the right arm of a power function. So keep in mind that we've looked at a cubic function. Cubic function with an unlimited domain would look like this. Right? As a power function with a limited domain of non-negative x's, it would only take the form of the right arm. If b is negative, then the shape of our power function graph actually looks more like this. And we'll talk more about that when we do rational functions. And the next type of function we're going to look at is an exponential function. Like a power function, an exponential function is made up of one term that contains a power, right? Both of these have a coefficient of a and then a power. What's different about an exponential function is that x is in the exponent, right? So in a power function, the base has x. In an exponential function, x is in the exponent. So this is an example of an exponential function. Our a value is 0.5, right? And the base of our power is 3. The graph of an exponential function looks a lot like the graph of a power function, except it typically crosses the y-axis at A. Okay, let's think about why that would be. Okay, we know that our y-intercept is going to occur, right? So our y-intercept is going to happen when x is 0. Right? If we plug 0 in for x, then we get f of 0 is 0.5 times 3 to the 0. Well, what is anything to the 0 power? It is 1. So this is 0.5 times 1, which is just 0.5, which is our value of A. So if I were to graph this function, my exponential function would cross the y-axis at 0.5, and it would curve upward, to the right, to the left. It would level off, approaching the x-axis as a horizontal asymptote. All right, couple more functions. Okay, we have an inverse variation function, like direct variation and a power function. An inverse function is made up of one term that will be of the form a constant over x, or a over x to the n. So this is an example of a power function, and the graph of this power function would look like this. Okay, this has two asymptotes. It has an asymptote, a horizontal asymptote along the x-axis, and a vertical asymptote along the y-axis. Okay. So finally, we come to rational functions. A rational function takes this form, right, where what we have on the top and the bottom, right, are polynomial functions. Okay, they could be linear functions, they actually could be constants, but the point is that to have a rational function, you would at least have x in the denominator. Typically, x shows up in both the numerator and the denominator. The graph of a rational function can have different features. So the graph of a rational function could simply look like our inverse variation function. That would be our simplest kind, right? But it could also be more complicated in that. So I could have a rational function that had a horizontal asymptote that is not the x-axis, but it is a different location, and a vertical asymptote that is not the y-axis, but at a different location. But the shape still typically takes a similar form, so it could look like this. The other thing that could happen is that sometimes rational functions have holes in them. We'll talk more about these when we get to rational functions later in the year. So again, to summarize, from this, you need to be very familiar with the names of these 8 functions, right? The names of these 8 functions, right? Be able to recognize an equation as, right, its appropriate function using its name, and be able to recognize its graph. So if I give you the name of a function, you should be able to match it with its graph or it's an equation. If I give you it's an equation, you should be able to give me its name and the typical graph. If I give you a graph, you should be able to give me its name and the general equation. So this ends part 1 of our Unit 1-2 notes.